Our modern world rests upon a fragile assumption about the past. We believe technology progresses in a straight line, that each generation builds upon the last. But scattered across the globe are silent, stone contradictions to that story. This is a journey through 25 ancient engineering puzzles that still stump the brightest minds of our era. By the end, you will see human history not as a simple timeline, but as a labyrinth of forgotten genius. How did a 2,000-year-old device predict cosmic events with clockwork gears? Why does a concrete recipe from ancient Rome outlast anything we build today? These are not just historical footnotes. They are direct challenges to our understanding of human capability. Each mystery we explore peels back a layer, suggesting our ancestors possessed insights we are only now struggling to rediscover. What does it say about us that the deeper we look backward, the more questions we find about our own place in time? That allure lies in a single, unsettling possibility. Perhaps our timeline of progress is not just incomplete, but fundamentally wrong. We look at a monument like the Great Pyramid and we see a tomb. But what if the builders saw something else entirely? A machine, perhaps, or a permanent statement written in geometry and aligned with the stars. This is the weight these puzzles carry. They are not just challenges of how something was built, but profound questions of why. Every strange alignment, every impossibly precise cut, every material that defies time is a message. And we have forgotten the language. Experts like archaeologist Sarah Parcak describe these sites as conversations. We ask a question with our lasers and satellites, and the stones answer with data that often leads to more questions. This dialogue across millennia forces a humbling realization. Our ancestors may have pursued knowledge along paths we abandoned long ago. They mastered their environment with a focus and ingenuity that can feel alien to our scattered, digital age. Their greatest works were not just products of labor, but of a deep, cultivated relationship with materials, with mathematics, with the very sky above. To solve these puzzles is to do more than unlock an ancient secret. It is to rediscover a forgotten dimension of human potential. So as we explore each enigma, listen for that silent conversation. The mystery is not in the stone alone, but in the mind that conceived it. Standing as the last of the ancient world's 7 wonders, the Great Pyramid of Giza does not ask for our wonder. It demands our humility. To stand before its 2.3 million stone blocks is to confront a scale of ambition that defies simple explanation. This is not merely a large building. It is a mountain crafted by human hands, and its first engineering puzzle is one of impossible orientation. The sides of the pyramid are aligned to the cardinal points with an accuracy within a fraction of a single degree. True north is not magnetic north, it is the axis of the planet itself. Achieving this alignment 4,500 years ago without modern instruments implies a mastery of astronomy that rewrites what we thought possible for the era. Some researchers point to the simultaneous transit of 2 stars, a method requiring years of patient observation and a theoretical grasp of celestial mechanics that seems out of place. It is as if the pyramid's foundation was laid not just in bedrock, but in the precise turning of the heavens. Then comes the question of movement. The logistics are staggering, a nightmare of project management that would challenge any modern construction firm. Each multi-ton block of limestone and granite had to be quarried, ferried across the Nile, and then lifted hundreds of feet into the air. The traditional theory of long, straight ramps requires more material than the pyramid itself, a paradox that has never been fully resolved. Alternative ideas suggest internal, spiraling ramps, or even a system for somehow softening the stone to make it more malleable, a lost technique hinted at in a few fragmented texts. But no single theory satisfactorily answers the sheer, elegant speed suggested by some timelines. It was not a project of centuries, but of a single generation. This points to a society with organizational genius, a seamless coordination of labor, resources, and engineering that feels almost alien in its efficiency. But the deepest mystery may be locked inside. The pyramid's internal chambers and narrow, angled shafts are not random. The king's chamber shafts align with specific stars, Sirius and the constellation of Orion, as they would have appeared in the sky 2,500 years before the Common Era. The Grand Gallery, with its soaring, corbelled ceiling, exhibits acoustic properties that some researchers believe were intentional. This accumulation of precise features, astronomical, geometric, and perhaps even sonic, points to a purpose that transcends the tomb theory. It suggests the pyramid was a machine for something, a permanent instrument designed to interact with cosmic forces or to encode fundamental knowledge about the world. The puzzle of the Great Pyramid, therefore, is threefold. How was it aligned? How was it built? And most hauntingly, why was it designed with such layered complexity? It stands as a silent rebuke to our assumptions, a Bronze Age project that still challenges the limits of modern engineering. Yet if the Great Pyramid represents a mastery of scale, another site whispers of a mastery of detail so fine it borders on the impossible. Journey to the windswept Bolivian highlands, over 2.5 miles above sea level, and you will find the scattered ruins of Puma Punku. It is a place that does not look ancient. It looks for all the world like the gutted remains of a modern factory, its components shattered by some colossal force. The puzzle here is not one of mass, but of micron-level precision lost in time. The building blocks of Puma Punku are not rough-hewn stone. They are andesite and red sandstone, some of the hardest stones on the continent, shaped into forms that defy the presumed technology of their era. We see H-shaped blocks with razor-sharp, interlocking grooves that fit together like pieces of a giant stone puzzle. We find surfaces so flat and smooth they could be mistaken for polished metal, and perfect right angles achieved with a consistency that suggests the use of precision guides, not hand tools. The geometric complexity is stunning. Channels and recesses are cut with a uniformity that implies prefabrication, as if these stones were mass-produced components designed to be assembled and disassembled. This modularity points to a sophisticated, standardized system of measurement, a building code that modern researchers have tried and failed to fully crack. The central mystery is stark. How do you achieve this machined perfection with tools believed to be nothing more than stone hammers and soft copper chisels? Copper would blunt against andesite in minutes, making the intricate detailing we see a task of unimaginable, tedious labor. Yet the results show no signs of trial and error, only flawless execution. Some researchers speculate about the use of lost abrasive compounds, perhaps diamond-tipped tools, or even advanced vibrational techniques that could soften stone. But these are speculations born of desperation in the face of the evidence. The purpose of this intricate stone tapestry is another layer of the enigma. The precision seems far beyond what would be necessary for a simple temple or plaza. It suggests a functional assembly, perhaps a complex machine, a resonant chamber, or a cosmological model of incredible accuracy that we can no longer read. Puma Punku stands as a direct challenge to our narrative of technological evolution. It presents not a gradual progression, but a sudden, inexplicable peak of skill, a snapshot of an engineering methodology that appears, dazzles, and then vanishes from the archaeological record, leaving behind only these shattered, perfect pieces. But what if a civilization's greatest genius could fit in the palm of your hand? In the year 1900, sponge divers off the coast of a Greek island called Antikythera stumbled upon a shipwreck from the 1st century before the Common Era. Among the statues and pottery, they recovered a lump of corroded bronze and wood, so encrusted it seemed like meaningless debris. For decades, it sat in a museum drawer, a curiosity. Then researchers looked closer. X-rays and later advanced three-dimensional imaging revealed the truth. This was not a lump, it was a machine, a clockwork universe of at least 30 interlocking bronze gears, housed in a wooden case no larger than a shoebox. We now call it the Antikythera Mechanism, and it is the single most disruptive artifact ever found from the ancient world. It has been called the world's first analog computer, a title it earns with every gear tooth. This device, crafted around 100 years before the Common Era, could predict the positions of the sun and moon, forecast eclipses with astonishing accuracy, and even track the 4-year cycle of the Olympic Games. It modeled the irregular orbit of the moon, a complex motion known as the lunar anomaly, using a brilliant pin and slot gear system that effectively created a mechanical analog for the heavens' imperfections. The miniaturization and understanding of differential gearing displayed here would not be seen again in Europe until the sophisticated astronomical clocks of the 14th century. That is a gap of over 1,300 years. This one object shatters the smooth, upward curve of our technological timeline. It proves that the conceptual leap to mechanical computation, the idea that metal could mimic the mathematics of the cosmos, was not a product of the Renaissance or the Industrial Revolution, but was alive in the Hellenistic world. Yet for all we have learned, the mechanism guards its deepest secrets. We do not know who built it. The genius behind its design remains anonymous, though names like Archimedes or his school are whispered by historians. We do not know its full purpose. Was it a teaching tool for philosophers, a navigational aid for sailors, or a rich man's dazzling demonstration of cosmic knowledge? Most hauntingly, we do not know if it was a singular masterpiece or one of many. The ship carrying it was a Roman vessel, likely looting treasures from the Greek world. Was this mechanism a unique prototype, or was it merely one copy of a technology that was, for a time, understood? Its solitary existence is what makes the puzzle so profound. It is a signal from the past, a clear, intricate message that says our ancestors were capable of far more than their ruins often suggest. The Antikythera Mechanism forces us to ask a terrifying and wonderful question. If this was what one ship was carrying, what other wonders were lost, their gears stilled forever at the bottom of the sea? The Antikythera Mechanism proves that ancient genius could be miniature, but in the Bekaa Valley of Lebanon, a different kind of puzzle looms, one built on sheer, incomprehensible mass. The Roman temple complex of Baalbek is famous for its soaring columns, but the true mystery lies beneath your feet, in its foundation. Here, resting with impossible calm, are 3 limestone blocks known as the trilithon. Each one is a leviathan of cut stone, estimated to weigh 800 tons. That is the equivalent of 2 fully loaded jumbo jets, side by side. They are fitted together with a precision that leaves no space for a blade between them, raised over 20 feet high to form a seamless platform. Yet this feat of megalithic engineering is not even the site's most bewildering aspect. A short distance from the temple, still seated in its quarry, lies the stone of the pregnant woman. This single block of stone weighs an astonishing 1,000 tons, a mountain that was cut free from the bedrock but never moved. Its very existence deepens the enigma. The puzzle of Baalbek is a brutal question of physics and logistics. How do you quarry a 1,000-ton block without it fracturing under its own unimaginable weight? The stone shows clean, precise cuts, suggesting a method that controlled the release of stress in a way that modern quarrying, with its diamond-tipped saws and controlled explosives, would still find challenging. Then comes the greater mystery. How do you move an 800-ton block? The quarry is not adjacent to the temple. These stones had to be transported over a mile of uneven terrain, then lifted and positioned with hairline accuracy. Modern engineering would deploy crawler cranes, the largest in the world, which can just barely handle such loads on perfectly prepared ground. The Romans, or perhaps a pre-Roman civilization that first shaped the site, had no such machines. The theories are as massive as the stones themselves. Some suggest a system of colossal wooden rollers requiring a forest's worth of lumber and an army of laborers pulling in unison. Others propose a kind of rocking and pivoting technique, a slow, incremental dance of leverage that could have taken months per inch. The coordination required is staggering to contemplate, a symphony of ropes, ramps, and wooden frameworks directed by engineers who understood the limits of their materials in a way we have perhaps forgotten. But the presence of the 1,000-ton monolith in the quarry asks the most haunting question of all. If they could cut it, why did they stop? Was it a challenge that finally exceeded even their extraordinary capabilities? Or was it a demonstration piece, left deliberately to show future generations the scale of ambition that once walked here? Baalbek does not whisper of delicate gears. It shouts in the language of raw power and logistical mastery, a reminder that some ancient puzzles are not about subtlety, but about moving mountains literally and asking us how on earth they ever did it. But sound is an invisible architecture, one that can shape the mind as powerfully as any stone wall. Far from the colossal blocks of Baalbek on the sun-drenched island of Malta, an entirely different kind of ancient engineering reveals itself not to the eye but to the ear. Beneath the modern town of Paula lies the Hypogeum of Hal Saflieni, a three-level subterranean sanctuary carved from solid limestone over 4,500 years ago. This is not a cave, it is a meticulously engineered underground complex of interconnecting chambers, stairways, and halls, all hewn by hand with stone tools. Its visual artistry is stunning, with red ochre wall paintings and carved facades mimicking the temples above ground. Yet the true genius of the Hypogeum is something you cannot see. It is something you feel deep in your bones. Certain chambers within this labyrinth possess extraordinary acoustic properties. The most famous is the so-called oracle chamber. When a deep male voice speaks or chants at a specific pitch within this oval room, the sound does not simply echo. It resonates, amplifying and vibrating through the space with a physical intensity that can be felt in the chest and fingertips. The entire chamber seems to hum, transforming a human voice into something monumental and otherworldly. Scientific analysis has shown that this resonance occurs at a frequency around 110 Hz, a tone that, interestingly, falls within the range known to affect human brain activity, potentially altering states of consciousness. This presents a profound puzzle. Was this acoustic marvel a happy accident of the chamber's shape and size, or was it a feat of deliberate sonic engineering? The precision of the carving, the careful smoothing of the walls, and the specific geometry of the space suggest intention. To achieve such a targeted acoustic effect implies a sophisticated, empirical understanding of sound wave physics, of how vibrations interact with limestone, and how to sculpt rock to trap and amplify specific frequencies. This turns the Hypogeum from a silent tomb into a living instrument. Experts in the field of archaeoacoustics, who study the soundscapes of ancient sites, propose that this was a technology of experience. The space could have been used for rituals, for communication with what the builders believed was a spirit world, or for communal ceremonies where sound itself was the medium for transformation. The vibrations would have been a shared physical sensation, uniting participants in a way that words alone could not. This challenges our most basic assumptions about ancient engineering. It was not solely about defying gravity or achieving permanence. It could also be about harnessing an intangible force like sound, using architecture to create controlled sensory and psychological effects. The Hypogeum asks us to listen to history, not just look at it. In its echoing chambers, we find evidence that our ancestors were not just builders of things, but composers of atmosphere, engineers of the human spirit, using the very rock beneath their feet as their instrument. High in the Andes, the stones of Sacsayhuamán do not simply sit atop one another. They embrace. This fortress overlooking the ancient Inca capital of Cusco presents a sixth puzzle, one of impossible intimacy between colossal rock and empty air. The walls are built in a zigzag pattern, a defensive design, but it is the individual stones that steal the breath. These are not uniform bricks. They are gigantic, irregularly shaped blocks of diorite, a brutally hard stone, some weighing over 100 tons. Their forms are wildly complex polygons, some with as many as 12 distinct angles and faces, each one unique in all the world, and they are fitted together in a dry stone technique without a single drop of mortar. The joints are so precise that for centuries people have said not even a razor blade can slip between them. This is not poetic exaggeration. Modern engineers have confirmed the tolerances are often within 1 millimeter across surfaces many feet wide. The puzzle here is a paradox of softness and strength. How do you take the hardest of materials and make it conform with such gentle, seamless perfection? The presumed tools of the Inca stone hammers, bronze chisels, and abrasive sand seem laughably inadequate for the task. To shape a multi-ton block of diorite into a specific, complex polygonal shape with hand tools would be a lifetime's labor for a single stone, yet here are thousands, assembled into walls that stretch for hundreds of feet. The process defies our linear thinking. It suggests a methodology that was the opposite of our own. We would design a wall on paper, cut standardized blocks, and assemble them. The Inca, or perhaps the master masons of a much older culture that occupied the site, seem to have worked in reverse. They may have selected a giant stone, then meticulously shaped the next stone to fit perfectly against its unique contours, and then the next, in a slow, three-dimensional puzzle where every new piece was custom-made for the gap it filled. This required an almost supernatural spatial reasoning, an ability to visualize negative space and complex geometry in the mind's eye before a single blow was struck. But the true genius of Sacsayhuamán reveals itself not in stillness, but in violence. Peru is a land of earthquakes. The seismic waves that topple rigid, mortar-bound buildings are absorbed and dissipated by these ingenious walls. The irregular network of joints acts like a shock absorber, allowing the stones to shift and settle during a tremor before locking back into place. This is resilience engineered into the very fabric of the structure, a dialogue with the volatile earth written in stone. Modern stonemasons who attempt to replicate the technique, even with powered tools, find it nearly impossible to achieve the same combination of artistic fluidity and structural perfection. The walls of Sacsayhuamán stand as a testament to a different kind of knowledge, one rooted in deep observation of material and environment. It was not about forcing nature into a grid, but about listening to the stone and allowing it to find its own most stable, interconnected form. In these silent, embracing walls, we see an engineering philosophy that sought not to conquer the landscape, but to become an inseparable, resilient part of it. While stone endures, the greatest engineering can be a map written in the mind. Across the vast, empty expanse of the Pacific Ocean lies the seventh puzzle, a testament to human intellect conquering the planet's greatest wilderness. This puzzle has no walls, no gears, no quarried blocks. Its material is the living world itself, and its architects were the Polynesian voyagers. Their achievement is staggering. Starting from islands in Southeast Asia, they discovered and settled every habitable island across a triangle of ocean covering 10 million square miles. They found specks of land like Hawaii, New Zealand, and Rapa Nui, Easter Island, navigating distances that would make a seasoned modern sailor pause. They did this without magnetic compasses, without sextants, without any written charts at all. Their vessel was the double-hulled canoe, but their true instrument was a cultivated, holistic perception we now call wayfinding. This was cognitive engineering of the highest order, a complex dynamic system for processing environmental data. The night sky was not a static picture. It was a moving compass. Navigators memorized the rising and setting points of hundreds of stars, understanding that as you sail, your celestial guideposts shift, creating a mental star path to your destination. The day offered a different set of clues. They read the ocean as a textured map, specific wave patterns, refracted and rebounding from distant islands hundreds of miles away, created a recognizable swell signature that a trained navigator could feel through the hull of the canoe. The flight paths of certain seabirds at dusk revealed the direction of land. The color and shape of clouds on the horizon often betrayed the presence of an island lurking below. This was not a collection of separate tricks. It was a single, fluid science, an ongoing dialogue between the navigator and a universe of signs. For modern experts raised on GPS and satellite imagery, internalizing this system is a profound challenge. It requires a rewiring of perception, a surrender of technological dependency to achieve a deep, embodied knowledge. The revival of this art, most famously through the voyages of the traditional canoe hokulea, has proven its stunning efficacy. Sailing from Hawaii to Tahiti using only these ancient methods, modern crews guided by master navigators like Mau have not only reached their targets but have done so with a reliability that silenced early skeptics. Yet for every successful voyage, the deeper mystery remains. How was this vast library of knowledge built, tested, and passed down orally over generations without being lost? It represents a monumental investment in education and memory, a societal commitment to preserving a science that was both practical and sacred. The puzzle of Polynesian navigation, therefore, is more than historical. It is a mirror. It asks us what we have gained with our instruments and what we may have lost in our direct connection to the world. It shows that engineering is not always about what you build. Sometimes it is about how you learn to see. Fire is a primal force, one that consumes to exist. Yet the eighth puzzle presents us with a flame that seemingly defied this basic truth. In the sands of the Libyan desert, at the oasis temple of Jupiter Ammon, ancient historians like Plutarch recorded a wonder that burned for centuries. This was no ordinary fire. It was described as an eternal flame, a light that required no fuel, that illuminated the sacred space day and night without ever being tended. While such accounts are surely layered with poetic exaggeration, they point to a profound and widespread engineering challenge across the ancient world, the creation of a perpetual or seemingly perpetual sacred fire. The puzzle is not whether a flame literally burned forever, but how ancient priests and engineers achieved such legendary longevity, crafting marvels that straddled the line between practical technology and divine theater. The core of the mystery lies in identifying the clever, material solutions behind the myth. Experts looking at sites like Jupiter Ammon first turned to geology. Natural gas vents where methane or other hydrocarbons seep from the earth could provide a continuous fuel source. A simple stone conduit or ceramic pipe placed over such a seep could direct the gas to a ceremonial burner, creating a flame that would appear miraculous to worshippers, burning steadily until the geological source itself eventually shifted or depleted. This is a compelling answer, a direct harnessing of the Earth's own energy. Yet not every sacred site sat atop a gas field. For temples elsewhere, the solution had to be engineered. One fascinating possibility involves wick systems made from slow-burning, fibrous minerals. Asbestos, known to the ancient world as a strange, fire-proof cloth, could have been used as a wick soaked in a reservoir of oil or animal fat. The mineral's resistance to combustion would allow it to draw fuel and burn with a slow, steady consistency for astonishing lengths of time, perhaps weeks or months on a single filling, far beyond the capability of ordinary flax or cotton. This transforms the miracle into a feat of material science and maintenance, a secret known only to the temple's inner guardians. Beyond geology and clever wicks lies the realm of chemistry. Some researchers speculate about chemical compositions that could create exceptionally long-lasting flames. Certain salts or metal compounds, when added to a fuel, can alter the color and burn characteristics, potentially creating a slower, more stable combustion. The legendary Greek fire of later centuries, a terrifying nautical weapon, showed a mastery of incendiary chemistry that clung to water. While different in purpose, it demonstrates that the ancient and medieval worlds possessed a sophisticated, if often lost, understanding of how to manipulate fire's behavior. The eternal flame, then, might have been a carefully guarded recipe, a specific blend of oils, waxes, and additives that yielded a clean, enduring burn. This turns the temple sanctum into a laboratory where the goal was not destruction but sustained, awe-inspiring illumination. Ultimately, this enigma sits at a fascinating intersection. It blends geology, chemistry, and what we might call ritual engineering. The goal was not merely technical, but psychological and spiritual. The perpetual flame was a symbol of divine constancy, a focal point for faith, and a powerful tool for inspiring devotion. By creating a fire that seemed to defy nature's laws, the priests engineered a direct experience of the miraculous. The puzzle for us today is to peel back the layers of legend without diminishing the achievement. It challenges us to see these ancient wonders not as magic, but as applied genius, where a deep understanding of the natural world was used to craft profound moments of human wonder. In the quest to explain the eternal flame, we uncover not a deception, but a sophisticated form of communication, a language of light, fuel, and stone meant to speak directly to the human soul. The mastery of fire led to the taming of a far more stubborn element, metal. But in the ninth puzzle, we find a material so perfect, its recipe vanished from the world. For 1,000 years, the warriors and nobles of the Middle East and Europe spoke of Damascus steel blades in whispers of awe. These were not mere weapons. They were described as being flexible enough to bend in a semicircle and snap back true, sharp enough to slice a silk scarf floating on air, and strong enough to cleave through lesser swords without losing their edge. Their surface shimmered with a mesmerizing, watery pattern, like a frozen stream etched into the metal. This legendary performance was born from a material known as Wootz steel, a high-carbon crucible steel forged in ancient India and traded in ingot form. The puzzle is not that we cannot make good steel today. We can make steel far beyond the dreams of any medieval blacksmith. The mystery is that we cannot reliably make this steel using the methods and materials they had. The entire industrial process, from the specific iron ore mined in the Deccan Plateau, rich in trace elements like vanadium, to the unique clay crucibles used for melting, to the precise, slow cooling cycle that allowed carbon to form into microscopic structures, was a complete technological system. And by the 18th century, that system was gone. The knowledge evaporated, leaving behind only the exquisite blades themselves as proof it had ever existed. Modern science has dissected these blades with every tool at its disposal. Under electron microscopes, researchers discovered the secret of the watery pattern. It comes from carbon nanotubes and nanowires that formed within the steel, creating a composite material at the nanoscale, a feat we only learned to observe in the late 20th century. These structures gave the blades their legendary combination of hardness and resilience. Metallurgists can now, in laboratory conditions, recreate the pattern and even some of the properties. They can produce a bar of steel that looks like Damascus, but the historical puzzle remains stubbornly intact. How did ancient smiths, working without thermocouples or spectrographs, consistently produce this nano-engineered material on a forge scale? How did they control the variables, the exact temperature of the bloomery, the composition of the clay crucible that added key impurities, the rate of cooling often done in the open air or a warm slurry with such repeatable success. It was a craft honed by generations, a sensory science where the color of the glow, the sound of the hammer, and the feel of the metal were the only readouts. This loss is a profound lesson in the fragility of knowledge. It shows that technology is not just information, but embodied skill, a dance between hand, eye, material, and fire. We have the analysis, but we may have forever lost the art. The quest to reclaim the true Damascus steel is more than a metallurgical challenge. It is an attempt to have a conversation across time with masters who understood their medium in a way we can measure but not yet fully replicate. In their lost craft, we see a pinnacle of ancient materials science, a reminder that some forms of genius leave behind only beautiful, silent questions. But the greatest shelters are not built upon the earth, they are carved from its very heart. In the surreal, fairy chimney landscape of Cappadocia, Turkey, a door in the ground leads not to a tomb but to a hidden metropolis. This is Derinkuyu, a subterranean city plunging over 200 feet deep, a labyrinth of tunnels, dwellings, and chapels that could shelter an estimated 20,000 souls. The scale is not merely impressive, it is a complete reimagining of what a city can be. The 10th puzzle lies not in a single artifact or monument, but in the breathtaking totality of its underground design. The builders worked with tuff, a soft volcanic rock that is easy to carve but notoriously unstable for large excavations. Their first and most critical challenge was structural integrity. To prevent catastrophic collapse across 8 sprawling levels, they left vast, uncarved pillars of bedrock to act as natural supports, a brilliant understanding of load distribution achieved through intuition and experience, not mathematical formulas. Then came the breath of the city. Ventilation is the silent killer of underground spaces, yet Derinkuyu thrived. A network of over 50 meticulously engineered shafts, some reaching from the deepest chambers all the way to the surface, created a passive airflow system. These were not simple holes. Their placement and diameter were calculated to exploit differences in air temperature and density, drawing fresh air down and pushing stale air up in a constant, life-sustaining cycle. This reveals a profound grasp of environmental engineering, of treating the Earth itself as a living system to be managed. Security was engineered with equal ingenuity. The city could be sealed from the inside by massive, circular rolling stone doors. Each one, weighing up to half a ton, was set into a carved groove and could be rolled across a corridor entrance with the strength of a few people, creating an impassable barrier. These were not just blocks of stone, they were precision components, their cylindrical shape and smooth grooves allowing them to move with a disturbing, silent efficiency. But a city is more than walls and air. It is a functioning society. Derinkuyu contained everything its inhabitants needed: stables for livestock, cellars for food, wineries, communal kitchens, churches, and even schools. A protected well, tapped deep into an underground water table, provided a secure supply even during the longest sieges above. The coordination required for this project defies easy explanation. Imagine the logistics of excavating millions of tons of soft rock without causing a collapse in another section. The planning for waste removal, for ensuring the ventilation shafts aligned with living spaces, for designing a water system that wouldn't flood the lower levels. All of this was accomplished without blueprints, without laser levels, without any of the tools a modern tunneling engineer would consider essential. For experts today, Derinkuyu is a masterclass in underground urban planning and geoengineering. It represents a holistic vision where every element, structural, environmental, and social, was integrated from the start. The city was not dug and then adapted. It was conceived as a complete, self-sustaining refuge, a testament to a civilization that looked at the soft rock beneath their feet and saw not an obstacle, but an opportunity for sanctuary. In its silent, deep halls, we find an ancient answer to one of humanity's oldest questions. How do you build a world safe from the storms above? Their solution was to turn inward, and in doing so, they created one of the most comprehensively planned environments the ancient world ever produced. The silence of a hidden city gives way to the profound isolation of the world's most remote inhabited island. Here, on the windswept grasslands of Rapa Nui, the 11th puzzle stands frozen in mid-stride. The giant stone moai, with their solemn, elongated faces, are icons of mystery, but the greatest enigma is not their creation nor their purpose, it is their journey. How did the Rapa Nui people, with a population never exceeding a few thousand, move these colossal figures, some weighing over 80 tons, across miles of rugged, volcanic terrain from the quarry at Rono Raraku to their coastal platforms, or Ahu? This is a puzzle of pure physics and human ingenuity, a logistical nightmare that modern engineers are still trying to solve with the island's limited resources. For decades, the dominant theory involved elaborate sledges and log roads, a process that would have consumed vast quantities of the island's precious palm timber. Yet in recent years, a radically different idea has taken physical form, one that seems to step right out of local oral tradition. This is the walking theory. Imagine teams of rope pullers not dragging a prone statue, but rocking a standing moai forward in a controlled, swaying gait. In a compelling experiment led by archaeologists Terry Hunt and Carl Lipo, along with a team from National Geographic, they demonstrated it was possible. Using a concrete replica and 3 teams of ropes, they showed how a moai could be walked upright by carefully coordinating pulls from the sides and back, allowing the statue to pivot on its curved base and rock forward in a series of small, deliberate steps. The visual is astonishing, giving life to the islanders' own stories that the statues walked to their places. This method is elegant in its simplicity, requiring far fewer logs and potentially less manpower than a massive dragging operation. It leverages the statue's own center of gravity and momentum, turning its immense weight from a burden into a tool, but the theory remains fiercely debated. Critics point to the undeniable archaeological evidence of prepared roads, some with clear wear marks. They argue the island's statues are found in various states of collapse along these ancient paths, which seems to suggest a different mode of transport. Could the truth be a hybrid approach? Perhaps the statues were moved in a horizontal position on sledges for part of the journey, then stood and walked for the final, delicate positioning. Each method presents its own engineering challenges. The sledge method demands an immense investment in wood and labor to create a smooth track. The walking method requires exquisite coordination and carries the constant, hair-raising risk of a catastrophic tip. Both theories force us to confront the same core puzzle: the breathtaking resource management of a society on a remote, ecologically fragile island. Every log cut, every calorie of food for the work crews, every rope fashioned from island fibers represented a significant investment. The transport of the moai was not just a construction project. It was the central organizing principle of their culture, a monumental act of faith and community that channeled their collective energy into a permanent stone testament. For modern experts, the challenge is to replicate the feat not with modern machinery, but with the same constraints the Rapa Nui faced. It is a case study in applied physics, where the solution lies not in advanced technology, but in a deep, intuitive understanding of leverage, balance, and human rhythm. The moai, therefore, are more than silent sentinels. They are captured motion, a snapshot of an ancient society solving one of the most difficult problems in pre-industrial engineering. Their journey from quarry to coast stands as a powerful reminder that human ingenuity, when focused by shared purpose, can accomplish what seems from a distance to be utterly impossible. A map can be a ghost of lost knowledge. In the year 1513, Ottoman admiral and cartographer Piri Reis compiled a world map from over 20 source charts, some dating back to the time of Alexander the Great. What survives is a tantalizing fragment, a parchment snapshot of the Atlantic Ocean showing the coastlines of Europe, Africa, and South America with a detail that feels eerily out of place. But the map's true controversy lies at its southern edge. There, below the Atlantic, the Piri Reis map depicts a landmass with a distinct, craggy coastline. Modern scholars identify it as the northern edge of Queen Maud Land, a part of Antarctica. This presents the 12th puzzle, a cartographic impossibility. Antarctica was not officially sighted until 1820, over 3 centuries after this map was drawn, and its coastline has been buried under a mile of solid ice for at least 6,000 years. How could a 16th century admiral draw a continent humanity had not yet found and show it seemingly ice-free? The map's own notes offer a clue, yet deepen the mystery. Piri Reis wrote that he used a source map from the 4th century before the Common Era, one that showed the entire inhabited world. This suggests his work was not original survey, but the compilation of far older geographic knowledge, a last echo from an ancient library that has since crumbled to dust. For modern experts in historical geography, the debate is fierce. Skeptics propose the southern land is a lucky artistic flourish, a misplotted Patagonia, or a theoretical terra australis that medieval scholars believed balanced the northern continents. They argue the apparent accuracy is a coincidence, a Rorschach test where we see what we want to see. Yet the proponents of the map's authenticity point to specific technical details. The map uses a sophisticated circular projection, and the distances between continents, while not perfect, reflect an understanding of longitude that should not have existed in 1513. Most compellingly, the depicted Antarctic coastline, when compared to modern seismic surveys of the bedrock beneath the ice, shows uncanny similarities to the actual, hidden topography. This is the heart of the enigma. If it is not a guess, then it implies a pre-modern civilization. Perhaps the source culture Piri Reis cited possessed the means and the motive to map a continent during a warm period in the distant past, preserving that data through copies and translations for millennia until it reached an Ottoman admiral's desk. The puzzle of the Piri Reis map, therefore, is not about ink on parchment. It is about the lifespan of information. It forces us to ask how knowledge survives the collapse of the societies that create it. Was this map a singular, fragile thread of data that somehow slipped through the sieve of time? Or is it evidence of a once global network of exploration whose records are almost entirely lost? It challenges our neat timeline of discovery, suggesting that the age of exploration was not a beginning but a rediscovery. In this single, fragile sheet, we confront the haunting possibility that the world was charted long before we ever thought to look. While we search maps for lost continents, the most enduring answers are often mixed into the mortar beneath our feet. The 13th puzzle is not a grand monument or a lost device, but a humble, ubiquitous material that has outlasted empires. Roman concrete. In our modern world, we expect concrete to decay. Our bridges, our highways, our buildings show cracks and spalling within decades, victims of water, salt, and the relentless freeze-thaw cycle. We pour millions of tons of it, knowing it has a limited lifespan. Now, stand beneath the dome of the Roman Pantheon. This vast, unsupported concrete ceiling was poured in the 2nd century, and it has not leaked, not sagged, not crumbled for over 2,000 years. Even more astonishing are the Roman harbors like the one at Portus, submerged in the corrosive seawater of the Mediterranean for 2 millennia. These concrete structures have not weakened. They have actually grown stronger. This is not a metaphor. Scientific analysis confirms that the concrete in these marine environments has continued to chemically react over centuries, becoming more resilient with time. For modern materials scientists, this performance is nothing short of revolutionary. The puzzle was not just what was in it, but how it worked on a microscopic level. The breakthrough came from looking at the material not as a dead paste, but as a living system. The Romans used a specific recipe. Instead of the Portland cement that forms the basis of modern concrete, they mixed a volcanic ash from the Pozzuoli region, called pozzolana, with lime and chunks of rock aggregate. But the recent crucial discovery was in their mixing method. They used hot mixing, incorporating quicklime directly into the mortar. Quicklime is highly reactive, and for years, experts thought its use would create unstable, brittle concrete. They were wrong. The Romans' method created tiny, white mineral inclusions throughout the mix, little lumps of reactive lime called lime clasts. For centuries, these were dismissed as sloppy mixing, evidence of poor quality control. Modern scanning electron microscopy revealed they were the secret weapon. When a tiny crack forms in the ancient concrete and water seeps in, it reaches these lime clasts. The water triggers a chemical reaction, dissolving the lime and allowing it to flow into the crack. There it recrystallizes, forming new calcium carbonate minerals that literally glue the fissure shut. The concrete heals itself. This is an ancient material with a built-in repair system, a technology we are only now beginning to comprehend. The full chemical complexity of the Roman recipe, the precise ratios and the nuanced understanding of geochemistry it implies, remains an active puzzle. It suggests the Roman engineers were not just following a formula, but deeply understood the behavior of their materials over geological timescales. Today, this ancient knowledge is urgently relevant. Modern cement production is a massive contributor to global carbon emissions. Creating more durable concrete that lasts for centuries, not decades, would be a monumental environmental breakthrough. Major cement companies and university laboratories are now racing to reverse engineer the Roman process, trying to create a modern equivalent that incorporates these self-healing properties. The goal is to build seawalls that fortify themselves against rising oceans and infrastructure that maintains itself for generations. So this ancient puzzle is unique. It is not a mystery locked in the past. It is an active conversation between antiquity and the future, where the solution to a very modern crisis, sustainability and resilience, might be found in the chemical wisdom of 2,000-year-old harbor walls. In the silent strength of Roman concrete, we find a legacy that is still setting, still hardening, still teaching us how to build a world that lasts. Stonehenge is a sentence written in stone, but we have forgotten its grammar. While the iconic circle of sarsen stones captures the imagination, the true puzzle extends far beyond the central ring. This is not a standalone monument, but the heart of a vast engineered landscape. A network of processional avenues, burial mounds known as barrows, and enigmatic circular pits called the Aubrey, holes all form part of a single, integrated design, constructed and modified over more than 1,000 years. The famous alignment where the heel stone frames the rising sun on the summer solstice is just the most obvious clue. It is the opening line of a much longer story written across the Salisbury Plain. The central enigma is one of purpose and persistence. What compelled generation after generation to return to this site, to haul blue stones from mountains over 150 miles away, to reshape the earth and stone in a project that spanned centuries? This was not a sudden construction. It was a slow, deliberate conversation with the sky, with each phase of building reflecting a deepening or shifting understanding. The puzzle for modern archaeoastronomers is to listen in on that conversation. They use sophisticated software to digitally wind back the clock, reconstructing the precise patterns of stars, sun, and moon as they would have appeared 4,000 years ago. This reveals a potential web of alignments far more complex than a single solstice sunrise. Certain stones and avenues may point to the winter solstice sunset, or to key lunar standstills, the extreme points on the horizon where the moon rises and sets over an 18.6-year cycle. Some researchers, like astronomer Gerald Hawkins, proposed that the arrangement of the 56 Aubrey holes could be used as a primitive eclipse predictor, a stone computer for forecasting celestial events that would have seemed terrifying and divine. This idea, while debated, highlights the profound question at Stonehenge's core. Was it a calendar, a temple, a healing site, or all of these at once? The greatest challenge in deciphering it comes from its builders themselves, a pre-literate society that left no written manuals. Their knowledge system was encoded directly into architecture and passed down through oral tradition, a living science that vanished when the culture that sustained it changed. This forces modern interpreters into a delicate dance. They must avoid imposing our own modern separation of science and spirituality onto a people for whom tracking the heavens was both a practical necessity for agriculture and a sacred duty. The alignments were likely not just for observation but for ceremony, marking times when the veil between the earthly and cosmic realms was believed to be thinnest. So the puzzle of Stonehenge is multidimensional. It is an engineering feat of moving megaliths, a surveyor's masterpiece of landscape design, and a cryptic astronomical text. Each attempt to crack its code, whether through laser scanning, soil analysis, or celestial modeling, brings us closer to understanding the worldview of its creators. Yet the stones retain their silence, reminding us that some ancient knowledge was meant to be experienced under the open sky, not decoded in a laboratory. In their patient alignment, we see a civilization that sought not to conquer nature, but to find its rhythm and build their world in harmony with its eternal, turning dance. Water is the lifeblood of civilization, yet its scarcity can be the end of it. In the vast, sun-baked plateaus of ancient Persia, where rainfall was a rare gift, survival demanded more than just finding water. It required a genius for moving it across impossible distances without losing a single drop to the thirsty sky. The 15th puzzle is not a silent monument, but a hidden, flowing artery beneath the desert. It is the Qanat, a masterpiece of subterranean logic that turned barren landscapes into blooming gardens. This was not a simple ditch. It was a gently sloping tunnel carved through rock and soil, often for dozens of miles. It began at the foot of a mountain where builders tapped a hidden aquifer, a reservoir of water trapped deep within the earth. From there, the tunnel sloped with a gradient so slight it seems imperceptible, perhaps only a few feet per mile, carrying water by the unerring pull of gravity alone, all the way to a perished city or farmlands below. The water flowed in cool, perpetual darkness, completely shielded from the evaporating sun. The construction itself is a staggering feat of communal labor. Teams of workers, known as mukanis, dug a chain of vertical shafts down from the desert surface, each one spaced about 100 feet apart, plunging sometimes hundreds of feet deep to reach the proposed tunnel level. These shafts served as air vents, excavation points, and a permanent maintenance ladder for future generations. The debris from the tunneling was hauled up through these shafts, creating the distinctive lines of rubble mounds that still snake across the Iranian desert like stitches on the Earth's skin. For modern hydraulic engineers, the sheer scale of this underground network is breathtaking, but the true, enduring puzzle lies in the very first step. How did the ancient prospectors, without seismographs or ground-penetrating radar, locate a viable aquifer deep within a mountain's foothills? And once they found it, how did they plot that perfectly precise, minuscule gradient over miles of unseen, underground terrain to ensure the water would flow steadily, but not so fast as to erode the tunnel? The answer speaks to a deep, accumulated wisdom. Prospectors likely looked for telltale surface signs, certain types of vegetation, the presence of specific insects, or the dampness of soil in particular valleys. They may have used simple but effective tools like long, weighted cords to measure angles of descent, or perhaps even observed the behavior of fog or mist in mountain passes to infer underground water sources. The plotting of the gradient was an act of faith and geometry, a mental map projected across the landscape where a single miscalculation meant years of wasted labor. This was engineering as a sacred trust, a project that could take a lifetime to complete, begun for the benefit of children and grandchildren. The Qanat is more than a water channel. It is a social contract, a system that required and reinforced profound community cooperation for construction, maintenance, and fair water distribution. Its sustainable design, with zero energy input and minimal loss, is a lesson modern water-scarce regions are urgently relearning. In the silent, cool flow of a Qanat, we find an ancient dialogue between human need and environmental limits, a conversation in which the solution was not to conquer the desert, but to listen to its hidden whispers and guide its secret bounty to the light. A flowing river of information is the foundation of any great city. The Indus Valley civilization, flourishing over 4,000 years ago, built metropolises like Mohenjo-Daro and Harappa that rivaled their contemporaries in Egypt and Mesopotamia. Their engineering was precise and systematic. They used standardized kiln-fired bricks in a uniform ratio, creating a modular building system across hundreds of miles. They designed the world's first known urban sanitation networks, with covered drains and private baths in homes, all connected to a main sewer. They constructed massive, ventilated granaries for food storage. This was clearly a society of extraordinary urban planners, a civilization that ran like a well-oiled machine. Yet the 16th puzzle presents us with a profound silence. Among the ruins, archaeologists have found thousands of small stone seals, exquisitely carved with images of animals and, most importantly, a series of mysterious symbols. This is the Indus script, and despite over a century of effort, no one alive today can read a single word of it. The engineering marvel here is not of mortar, but of administration. How do you coordinate the production of millions of identical bricks, manage the distribution of grain from central stores, or enforce the codes for drainage and construction across a vast territory without a system of written communication that we can comprehend? The puzzle is systemic. The very existence of such uniform, complex cities implies a sophisticated level of bureaucratic control, a shared language of governance that has left no manual behind, only these cryptic miniature seals. Most inscriptions are frustratingly short, just 4 or 5 symbols, often found on seal stamps that were likely used to mark clay tags on bundles of goods. This suggests they were not for literature or history, but for practical, economic transactions, a form of ancient branding or administrative shorthand. The seals themselves, with their unicorns, bulls, and ritual scenes, might have denoted a family, a trade guild, or a specific commodity, but without a key, we are left guessing. Modern experts have turned to the most advanced tools of our time to break this ancient code. Computational linguists and data scientists feed high-resolution images of the symbols into algorithms, searching for statistical patterns in the order of characters, their frequency, and their placement. Artificial intelligence attempts to model the script's underlying grammar and structure, comparing it to known languages in the hope of finding a hidden kinship. But the core challenge remains the same one faced by the decipherers of Egyptian hieroglyphs before the Rosetta Stone. Without a bilingual text, a clear link between the unknown script and a known language, even the most powerful computer hits a wall. The script may not represent a spoken language at all, but a system of ideograms or a complex mix of sounds and ideas unique to their culture. This makes the Indus Valley civilization uniquely haunting. We can walk their grid-patterned streets, marvel at their advanced plumbing, and hold their beautiful seals in our hands, yet we cannot hear their voices. We see the output of their collective mind in the ordered geometry of their cities, but the instructions, the laws, the daily ledgers that made it all possible are locked away in a cipher. The silent seals are a testament to a lost form of genius, one that mastered the engineering of society itself, leaving behind a perfect, functional skeleton of a civilization whose thoughts we may never fully know. 17 lines across the desert floor stretch for miles, straight as a laser beam. From ground level, the Nazca lines are a confusing network of shallow trenches, but ascend to the sky and the truth reveals itself. These are not paths, they are colossal drawings, a hummingbird with wings spanning the length of a football field, a spider with legs that curve for hundreds of yards. A perfect spiral, a triangle, a trapezoid, all etched into the arid Peruvian plain by the simple act of removing a layer of dark, sun-baked pebbles to expose the lighter, chalky soil beneath. The engineering puzzle here is one of perspective. How do you design a perfect, symmetrical monkey when you can never see more than a few feet of it at a time? The Nazca people created these geoglyphs between 500 years before the Common Era and 500 years after, and they did it without flight, without drones, without any means to check their work from above. The precision is staggering. Many of the straight lines run true for over 10 miles, deviating by less than a few yards over their entire length. The curves of the animal figures are smooth and proportional, their forms recognizable from thousands of feet in the air. This implies a design process that was methodical and mathematically sound, a transfer of a small-scale model to a gigantic canvas using only the tools at hand. The most plausible theory involves a system of master planning and simple surveying. A small-scale drawing could have been made on a grid, with each square then translated to a much larger grid, marked out on the desert floor using a network of stakes and ropes. By clearing the pebbles along the lines dictated by these oversized coordinates, teams of workers could create the image section by section, guided by a foreman who held the master plan but could never witness the full picture taking shape. Yet for modern experts attempting to replicate the technique, the challenge is profound. The terrain is not flat. It is a rolling desert with hills and gullies that distort sight lines. Maintaining a perfectly straight bearing or a consistent curve over such distances, across such uneven ground, requires an advanced understanding of geometry and an almost ritualistic patience. A single misplaced stake, a rope stretched a degree off true, and the entire figure would distort into nonsense. This points to a society with not just artistic vision, but with disciplined, communal coordination and a deep trust in the process. But the how is only half the mystery. The why adds a deeper, more haunting layer. What was the purpose of art that only the gods or the condors soaring on thermal winds could fully appreciate? Some researchers see an astronomical calendar with lines pointing to solstice sunrises or important star clusters. Others propose a connection to water, the most precious resource in the desert, with the shapes and lines mapping underground aquifers or serving as ritual pathways to invoke rainfall. The most compelling theories blend the practical and the spiritual. The lines may have been walked upon during ceremonies, a form of participatory worship where the act of traversing the giant image connected the people to the entity it represented, be it a life-giving spider associated with rain or a hummingbird symbolizing fertility. From the ground, it would have been a meaningful pilgrimage. From the sky, it would have been a breathtaking symbol. This duality is the heart of the Nazca puzzle. It forces us to expand our definition of engineering beyond pure function. Here, the product was not a tool, a shelter, or a machine. It was an experience, a message, and a permanent alteration of the landscape to serve a cultural vision that blended the earthly and the celestial. The lines are a reminder that ancient engineering could be an act of faith, a giant prayer written in the only language they believed the heavens would understand, the silent, perfect geometry of the earth itself. Sound is a language the ancient Maya may have carved in stone. At the Great Pyramid of Kukulkan in Chichen Itza, stand before the monumental staircase and clap your hands once. The echo that returns is not a simple repetition. It is a sharp, descending chirp, an uncanny mimicry of the sacred Quetzal bird, a creature deeply woven into Maya cosmology as a symbol of the sky and divinity. This is the 18th puzzle, a phenomenon that transforms a silent temple into a potential instrument. The effect is so precise and repeatable that it moves beyond coincidence for many researchers. It suggests the pyramid's design, the exact spacing and angle of its steps, was calculated to sculpt sound waves into a specific, meaningful pattern. This acoustic marvel is not isolated. At other Maya sites, like the circular observatory at Chichen Itza known as El Caracol, whispers can carry with unusual clarity across its interior, and at the palace of the governor at Uxmal, a person speaking from a specific spot can be heard clearly at a distant point, a primitive form of acoustic projection. These curious effects have ignited a compelling hypothesis. Could the Maya and perhaps other ancient cultures have been intentional sonic engineers, designing their sacred spaces not just for visual grandeur, but to harness and manipulate sound for ritual purposes? For modern acoustical physicists, the challenge is to distinguish between a happy accident of geometry and a deliberate feat of architectural science. The investigation involves complex digital modeling and on-site measurements. They map how sound waves bounce off the hard limestone surfaces, calculating frequencies and reflections to see if the structures act as natural amplifiers or filters for specific tones. The pyramid steps, for instance, form a periodic grating, a series of evenly spaced surfaces that can break a sound wave into distinct frequencies, much like the grooves on a record. A handclap contains a broad spectrum of noise, but the geometry of the stairs could be filtering out all but that Quetzal-like chirp. This implies a sophisticated, if intuitive, understanding of sound physics. It suggests generations of observation, where builders noted how certain proportions and angles in smaller structures created interesting echoes, and then scaled up those principles into their most monumental works. The purpose of such engineering would have been profoundly spiritual. In rituals, the replicated call of the Quetzal bird emanating from the pyramid itself would have been a powerful demonstration of the temple's living connection to the spirit world. It would transform a ceremony from a silent observance into a participatory dialogue with the architecture, where sound became the medium for communion. The steps become a giant keyboard, the chambers a resonant chamber, turning the entire site into a sacred instrument played by the wind, the rain, or the movements of the people themselves. This sonic layer adds a new dimension to our understanding of ancient genius. It reveals a holistic design philosophy where aesthetics, astronomy, and acoustics were not separate disciplines, but intertwined threads in a single tapestry of meaning. The pyramids were not just mountains pointing to the stars. They may have been voices engineered to speak in the language of the gods, leaving behind an echo we can still hear today, a whispered clue to a culture that listened as intently as it looked. The echo of a sacred bird fades into the clash of steel in a frozen north. From the mists of the Viking Age, another blade emerges, not with a watery pattern, but with a name that became a legend. The Ulfbert sword, forged between the 9th and 11th centuries, these weapons were not just tools of war. They were technological anomalies so far ahead of their time that they rewrite our understanding of medieval metallurgy. When archaeologists first analyzed them, they expected the typical wrought iron of the era, a material prone to bending and shattering. What they found was shockingly pure steel. This was crucible steel with a carbon content around 3 times higher than that of their contemporaries, making the blades remarkably strong, flexible, and capable of holding a lethally sharp edge. The signature was a frank inscription inlaid into the blade, plus ULFBERHT, a maker's mark that became a brand synonymous with supreme quality. The puzzle of the Ulfbert is not a question of local genius alone, but of a mysterious global pipeline. How did this hyper-advanced material end up in the hands of Scandinavian smiths? Europe at this time simply did not possess the technology to produce steel of this purity on a consistent scale. The answer points east, along the vast river trade routes that connected the Viking world to the caliphates of the Islamic world and the workshops of Central Asia. There, masters had perfected the crucible steel process, creating ingots of high-carbon wood steel, the very same material that would become legendary Damascus steel. It is likely that Viking traders navigating the Volga and the Dnieper acquired these raw steel ingots as a premium trade good, transporting them thousands of miles back to northern forges. Yet acquiring the material is only half the story. The true enigma lies in the forging. The Viking smiths who worked these exotic ingots possessed a masterful, localized skill. They had to understand how to heat, fold, and hammer this unfamiliar steel without ruining its delicate carbon structure, a process requiring an intuitive grasp of temperatures and techniques that their neighbors did not have. This combination is what makes the Ulfbert so fascinating. It represents a moment of technological convergence where a global supply chain met localized artisan mastery. The swords were not imported finished products. They were the result of a Viking smith interpreting and executing a foreign material science with breathtaking competence, creating a weapon that would not be equaled in Europe for nearly 1,000 years until the furnaces of the Industrial Revolution. The Ulfbert, therefore, is more than a sword. It is a relic of a connected ancient world, a physical testament to the fact that ideas and materials traveled vast distances, and that innovation often sparks at the intersection of different streams of knowledge. In its cold steel, we see not an isolated people, but savvy participants in a network that spanned continents, turning imported potential into legendary, enduring strength. The Antikythera Mechanism fits in the palm of your hand, but its purpose opens a door to an entire lost world. We have marveled at its gears, decoded its functions, and stand in awe of its complexity. Yet the 20th and perhaps most profound puzzle asks a simpler, deeper question. Why did it exist at all? This is not a query of engineering, but of human intention. Was this intricate bronze universe a philosopher's teaching tool, a wealthy patron's dazzling conversation piece, a navigator's practical guide, or a priest's instrument for casting horoscopes? Each possibility paints a different picture of the society that created it, forcing historians to place a device of anachronistic genius into a cultural context we thought we understood. The funding alone is a mystery. The resources and skill required to craft such a device were immense, implying a powerful sponsor, perhaps a royal court or a major philosophical school, investing in a project that blended art, science, and spectacle. This was not a mass-produced item. It was a masterpiece, so what worldview did it embody? The mechanism's very existence suggests a Hellenistic culture where the cosmos was not just observed, but seen as a comprehensible mechanical system. Turning a handle to see the moon's phase or an eclipse's date would have made abstract astronomical theories tangible, transforming philosophy into a physical experience. It could have been a powerful tool for astrology, which the Greeks saw as a serious science linking celestial patterns to earthly events. Predicting planetary positions with a crank would give a practitioner an air of divine authority. Alternatively, imagine it in a public square or a temple, operated by a scholar to demonstrate the orderly, predictable nature of the heavens to citizens. A stunning propaganda tool for a worldview based on reason and cosmic law. This device challenges the narrative that advanced mechanical models were a product of the later Renaissance. It forces a re-evaluation of ancient Greek intellectual life, revealing a society that may have used such models not just for calculation, but for education, for ceremony, and for reinforcing a fundamental belief that the universe, in all its complexity, could be held in your hands and understood. The true puzzle of the Antikythera is not just how its gears turned, but how it turned the minds of those who beheld it, offering a glimpse of a sophistication that humbles our timeline of progress once more. A standard unit of measure is the silent language of any great building project. Now, imagine that same language being spoken from the windswept moors of Scotland to the chalk downs of southern England, across hundreds of miles and centuries. This is the 21st puzzle, a ghost in the geometry of stone circles. In the mid-20th century, engineer and archaeologist Alexander Thom surveyed hundreds of Neolithic sites across Britain and France. After meticulous analysis of their dimensions, he proposed something astonishing. These ancient builders, he argued, were not placing stones at random or by rough estimation. They were using a precise, standardized unit of measurement. He called it the megalithic yard, equivalent to about 2.72 feet, or 83 centimeters. The implications of this are profound. If Thom was correct, it suggests a shared system of engineering mathematics across a vast swath of prehistoric Europe, a continent we often picture as fragmented into isolated tribal groups. The puzzle for modern experts is not whether these sites were carefully planned, that is clear. The debate is whether this specific, consistent unit is a real, intentional standard, or a statistical mirage born from our own desire to find order. Proving a standardized measurement from over 5,000 years ago is a formidable challenge. Metrologists and archaeologists dive into the data, examining the diameters of stone circles, the spacing between monoliths, and the layouts of burial mounds. They ask if the recurring appearance of multiples and fractions of 2.72 feet is too consistent to be coincidence. Some compelling sites, like the Ring of Brodgar in Orkney, seem to be laid out in perfect integer multiples of this unit. But skeptics argue that with enough measurements from enough sites, some pattern is bound to emerge by chance. They point out that natural human pacing could produce roughly consistent lengths, or that the unit might derive from a common, practical method available to all. One fascinating theory involves the simple pendulum. A pendulum with a cord exactly half a megalithic yard in length swings with a beat remarkably close to 1 second. This could have provided a reproducible way for separate communities to derive the same standard, not through direct communication but through shared empirical physics. They wouldn't need to trade rulers, they would just need to observe the same rhythm of a swinging stone. Yet, even if the standard emerged from such a universal method, its widespread application in monumental architecture remains a puzzle. It implies a shared conceptual framework, a common understanding that when you built a sacred space, you did so according to a cosmic or communal rulebook written in numbers. This points to a level of intellectual exchange and shared purpose among Neolithic cultures that we are only beginning to appreciate. It hints at traveling master builders, or the pilgrimage of knowledge along ancient trade routes where the secret was not the stone but the measure. The concept of a pan-European standard millennia before the Roman foot or the metric system forces a quiet revolution in how we see prehistory. It suggests collaboration and shared vision on a continental scale, a network of minds aligned not by empire but by a common pursuit of celestial and earthly harmony. In the silent spacing between ancient stones, we may be detecting the faint but precise echo of a forgotten standard, the first draft of a language all of Europe once understood. Iron does not surrender to time quietly. It speaks in a slow, orange whisper of decay, a process we accept as inevitable. Yet in the heart of Delhi, a silent sentinel has defied that fate for over 1,600 years. The iron pillar, erected around the year 400, stands 7 meters tall as a stark contradiction. It has endured 16 centuries of scorching heat, pollution, and most critically, the relentless monsoon rains that should have reduced it to a crumbling relic. Its surface is smooth, bearing only a dark, protective patina, with none of the flaking, destructive rust that plagues modern steel structures within decades. This is the 22nd puzzle, a metallurgical miracle achieved centuries before the science of corrosion was even conceived. Modern forensic analysis has peeled back the layers of its secret. The pillar is forged from remarkably pure wrought iron, but its true guardian is an unexpected element, a high phosphorus content. This phosphorus, along with small amounts of other elements from the specific ores used, promoted the formation of a thin, stable film on the metal surface. Scientists call this compound mesowite, a barrier only a few hundred atoms thick that acts as a perfect shield. It prevents oxygen and moisture from reaching the raw iron beneath, effectively putting the corrosion process into a permanent, passive sleep. The central enigma for historians of science is one of intent. Did the master smiths of the Gupta dynasty deliberately engineer this anti-corrosion property, or was it a spectacularly fortunate accident born from their unique local materials and smelting techniques? The process they used involved a high-temperature forge welded from many individual pieces, using iron ore that naturally contained phosphorus. They would have had no knowledge of atomic layers or electrochemical reactions. What they did possess was a profound empirical wisdom. Through generations of trial and observation, they would have learned that iron produced from certain mines, treated in a certain way in the forge, resulted in metal that lasted. They were not designing mesowite, they were perfecting a recipe for permanence, and the compound was the magnificent byproduct. In this way, the pillar stands as a dialogue between ancient craft and modern chemistry. Our stainless steels, engineered with precise additions of chromium, strive for the same result through controlled, laboratory-born science. The ancient smiths arrived at a comparable endpoint through the slow, patient language of material and fire. Their achievement forces us to reconsider the boundaries of empirical knowledge. It shows that a deep, intuitive relationship with a process can yield results that look, from a distance, like magic or impossible foresight. The iron pillar does not boast, it simply endures, a quiet lesson in humility for any engineer who walks past it today, reminding us that some of the most advanced solutions are not always invented, but sometimes discovered through a lifelong conversation with the elements. The Earth's memory is written in layers of silt and salt water. Off the coast of the Gulf of Corinth, beneath the quiet sea, lies the 23rd puzzle, the lost city of Helaik. In the winter of 373 before the Common Era, a powerful earthquake struck the region. The ground liquefied, and the city of Helaik, a prominent member of the Achaean League, slid as one piece into the waters of the Gulf. A tsunami followed, ensuring its complete submersion. For centuries, Helaik lived only in legend, a cautionary tale from ancient historians. But modern underwater archaeology has finally mapped its ruins, finding streets, building foundations, and harbor walls preserved in the seabed. This discovery presents a profound engineering mystery. The city was built in one of the most seismically active zones on Earth. Its citizens knew the ground could tremble and break. So what did they do about it? The puzzle of Helaik is not just its dramatic end, but how it stood for so long beforehand, and what its construction can teach us about ancient resilience in the face of inevitable disaster. Across Greece and Anatolia, ancient builders developed ingenious, intuitive methods to make their structures dance with the earth rather than fight it. They worked with a deep understanding of material behavior long before the science of seismology existed. One of the most widespread techniques was the use of flexible timber lattices within stone or brick walls. Imagine a wall built not as a solid, rigid block but as a composite. Stone courses were interlocked with horizontal beams of wood, creating a network that ran through the entire structure. This wooden skeleton acted as a shock absorber. During an earthquake, the timber could flex and bend, allowing the wall to sway and settle without catastrophic collapse. It was a literal lifeline woven into the fabric of their homes and temples. Another common adaptation was the use of double wall construction with a rubble core. Two finely crafted stone faces were built, and the gap between them was filled with loose rubble and earth. This filling acted as a damping material, dissipating the energy of seismic waves as they passed through the wall. The exterior stones might shift and grate against each other, but the core absorbed the violence, preventing a total structural failure. Builders also paid meticulous attention to foundations. They often used layered platforms of alternating materials: stone, clay, sand, and gravel, which helped to isolate the building from the worst of the ground's shaking. The famous columns of Greek temples were not fixed with mortar. They sat on stone pivots, allowing them to rock independently during a tremor before settling back into place, much like the stones at Sacsayhuamán. This was engineering through empathy with the forces of nature, not defiance. The goal was to create a structure that could live with the earthquake, to yield gracefully and survive. Hellike's builders almost certainly employed some, if not all, of these methods. Their city was a testament to generations of accumulated seismic wisdom, a collective memory of past tremors encoded in architectural practice. Yet Helike still fell. Its fate represents the ultimate test of that ancient technology, and its failure is as instructive as its longevity. The event that destroyed it was not a typical quake. Geological evidence suggests it triggered a catastrophic process of soil liquefaction, where water-saturated ground temporarily loses all strength and behaves like a liquid. The city's foundations, designed to handle shaking, could not withstand the ground literally turning to soup beneath them. The entire urban mass became a sliding raft on a fluidized layer destined for the sea. This reveals the limits of their engineering. Their methods were brilliant for dealing with vibrational energy, but they could not counter a complete failure of the substrate itself. The tsunami that followed was a final, unsurvivable blow. For modern experts in earthquake engineering, Helike is a sobering case study. It underscores a fundamental principle: the best structural design in the world can be defeated by the geology it sits upon. Today's engineers, building in places like San Francisco, Istanbul, or Tokyo, face the same core challenge as the builders of Helike: how to create resilience against the unpredictable. They use base isolators, tuned mass dampers, and flexible steel frames, which are the high-tech descendants of those ancient timber lattices and rocking columns. The ancient solutions were born of observation and embodied craft. Ours are born of computer modeling and material science, but the conversation is the same. How do you build a community that can withstand the Earth's raw power? Helike's ruins, silent under the sea, remind us that this is not a modern question, but a human one as old as settled life itself. Its loss was a tragedy, but its silent engineering legacy continues to inform the quest for a safer world, proving that even in failure, there are vital clues for those who know how to look. A whisper of power can be held in a simple clay jar. Among the dusty shelves of the National Museum of Iraq rests an artifact that seems to belong to a different century entirely. It is known as the Baghdad Battery, a modest assembly from the Parthian era, around 2,000 years old. The object is unassuming, a 5-inch tall ceramic vase, inside which sits a rolled copper cylinder, and within that an iron rod. The rod is suspended by an asphalt plug, carefully sealing the top and insulating the two metals from direct contact. To a modern eye, the configuration is unmistakable. If this jar were filled with an acidic liquid vinegar, grape juice, or even lemon juice, the electrolyte would react with the metals, creating a chemical reaction that generates a small electric potential. In essence, it becomes a primitive galvanic cell, capable of producing just over 1 volt of electricity. This is the 24th puzzle, and it ignites a controversy that crackles with possibility. Did an ancient civilization, 2 millennia before Volta's famous battery, intentionally harness electrochemical energy? The experiments are clear. Modern reconstructions, using replicas filled with common ancient acids, do produce a measurable, if faint, voltage. The device works, but proving it was used as a battery is an entirely different challenge, one that resides in the silent gaps of the archaeological record. No wires have been found alongside these jars, no conclusive evidence of electrical consumption, like electroplated objects with clear traces of this specific process, has been definitively linked to them. They are found in isolation, a solution in search of a problem, so the puzzle becomes one of interpretation. If it was a battery, what was its purpose? One compelling theory points to electroplating. The Parthians were master metalworkers, known for gilding silver objects with a thin layer of gold. The traditional method uses mercury, a dangerous and toxic process. Could a weak electric current from a bank of these cells have been used to achieve a similar, perhaps ceremonial, plating effect? It is a tantalizing idea, suggesting a clean, controlled technology lost to time. Other possibilities lean toward the experiential. A mild electric shock generated by such a cell could have been used for medicinal or therapeutic purposes, a form of ancient pain management or muscle stimulation that would have seemed magical. Or perhaps the purpose was purely spiritual. In a dim temple, a priest could have connected several of these jars in series to produce a stronger current. Touching the wires could induce a tingling sensation, interpreted as contact with a divine force, a tangible miracle engineered to inspire awe and faith. This last possibility touches the core of the mystery. How would an ancient people conceptualize this invisible force? They had no theory of electrons or circuits. Electricity would have been a mysterious phenomenon, perhaps linked to the same vital essence they saw in lightning or the strange numbness caused by certain fish. Their understanding would have been phenomenological. They knew it could be produced, and they observed its effects, even if the why remained a mystery. This artifact, therefore, forces experts to confront a radical idea. Innovation is not always a linear path from theory to application. Sometimes it is the reverse. A culture could have stumbled upon a useful effect through experimentation, perfected the apparatus that produced it, and employed it for generations within a specific cultural or ritual context, all without ever developing the abstract scientific framework we consider essential. The Baghdad Battery stands as a monument to that possibility. It may not represent a lost electrical grid, but it could very well signify a lost electrical practice. Its power lies not in the voltage it can produce, but in the questions it forces us to ask about the boundaries of ancient knowledge. It challenges us to consider that our ancestors might have been playing with forces we claim to have discovered, using a language of trial and observation we are only now learning to translate. In its silent clay form, it holds a charge far greater than 1 volt. It holds the electrifying possibility that the past was far more curious and far more clever than we have ever dared to imagine. The final puzzle lies not in the sky or the sea, but in the silent, dripping dark beneath a Chinese village. In the county of Longyu, what began as a curious local legend became a revelation that swallowed all expectations. In 1992, a farmer decided to pump water out of a small, waterlogged hole locals called a bottomless pond. After weeks of effort, the water drained away to reveal not a natural cavern, but something impossible, a vast hand-carved grotto of breathtaking precision. This was not a single discovery, it was the first of 24. These are the Longyu Caves, an underground complex of such staggering scale that it redefines the very meaning of a hidden project. Each cavern is a monumental space, some covering over 100,000 square feet, with ceilings soaring 10 stories high. They are not rough tunnels. They are finished architectural spaces with massive, sculpted pillars left in place to support the ceiling, sloped sidewalls, and vast, flat surfaces covered from floor to ceiling in a mesmerizing, uniform pattern of parallel chisel marks. The labor involved is almost incomprehensible. Modern calculations estimate that to create these 24 chambers, ancient workers would have had to remove approximately 1 million cubic meters of solid sandstone. That is a volume of rock equivalent to building 2 of the Great Pyramids of Giza from scratch. And here we encounter the first layer of the mystery, a question of pure physical logistics. Where did all that stone go? 1 million cubic meters of rubble is not something you can hide. It would form a mountain of its own, yet no such spoil heap exists in the local landscape. There is no record of it being used to construct a nearby city or fortification. It simply vanished as if the earth itself had swallowed the evidence of its own excavation. This missing mountain points to a project of astonishing organization, one that managed not only the digging but the complete and total disposal of its waste product, leaving no trace for future archaeologists to find. The second layer is the silence. Despite their colossal scale, there is not a single historical document, not one line of poetry or imperial record from any Chinese dynasty that mentions the construction of the Longyu caves. For a civilization famed for its meticulous record-keeping, this is a void as deep as the caves themselves. They were carved over 2,000 years ago, yet they appear in no known history, no tax ledger for labor, no account of a great public works project. This absence is deafening. It suggests the work was either so secret that it was deliberately erased from the official narrative, or so ancient that its memory faded before written history in the region began. The purpose of the caves is the third and perhaps most haunting puzzle. They show clear signs of architectural intent. The pillars are evenly spaced for structural integrity. The angles of the walls are consistent. The ubiquitous chisel marks are applied at a uniform, 60-degree angle across every surface, a signature of a single, disciplined technique used by countless workers over what must have been generations. This was not a haphazard quarry. It was a deliberate, designed environment, but for what? They lack the adornments of a tomb or a temple. There are no inscriptions, no altars, no artifacts left behind. Some researchers have proposed they were imperial stone quarries, but the care and finish of the interiors go far beyond what would be needed for mere resource extraction. Others suggest they were secret storage bunkers, or even ceremonial spaces aligned with spiritual beliefs we can no longer decipher. The sheer, empty grandeur of the halls suggests they were meant to be occupied, to be experienced, but by whom and for what ceremony remains locked in the dark. For modern experts, the Longyu caves represent the ultimate engineering ghost story. They are a project of state-level ambition that left no paper trail, a mountain of labor that left no debris pile, and a finished space that left no clue to its use. They force us to confront the limits of our historical knowledge. We can map every inch with lasers, analyze the tool marks, and calculate the manpower, but we cannot hear the orders that started the work or see the faces of the last workers to leave. The caves stand as a monument to a collective endeavor that chose, for reasons we may never know, to bury itself completely, leaving behind only these vast, beautiful, and silent questions in the rock. In their shadowed halls, we find the perfect, unsettling end to our journey, a reminder that the greatest mysteries are not always about what was built, but about all that was deliberately and perfectly forgotten. 25 silent witnesses stand across the globe, from the deep caves of Longyu to the high deserts of Nazca. We have walked beside them, listening for the echoes of the minds that built them. This journey reveals a pattern far more profound than any single mystery. These are not isolated errors in our historical record. They are a chorus, and together they sing a humbling truth about the nature of human progress. Our timeline is not a straight, ascending line. It is more like a spiral where knowledge is discovered, perfected, lost, and then rediscovered along a different path. The concrete of Rome outlasts our own. The steel of Damascus displays a nanotechnology we only recently learned to see. The navigators of the Pacific read a map written in waves and stars. Each case is a testament to a form of genius deeply attuned to its specific material, its environment, and its moment in the cosmic dance. They challenge the quiet arrogance of the present, the assumption that newer must always mean better, or that our tools grant us a monopoly on understanding. These puzzles remind us that innovation is not merely about having advanced technology. It is about having a profound relationship with the world you inhabit. It is about seeing the potential in a volcanic rock, in a star's position, in the resonant frequency of a carved chamber. Our ancestors were not primitive. They were specialists in resilience, in observation, in making the impossible routine with the tools they cherished. The greatest lesson these stones and gears offer is not about the past alone, but about our future. In an age facing crises of sustainability, of material waste, and of disconnection from the natural world, these ancient solutions speak directly to our needs. The self-healing concrete of Roman harbors points toward infrastructure that maintains itself. The passive, gravity-fed Qanat's model water management without a single watt of energy. The seismic flexibility of ancient temples whispers strategies for living with a restless planet, not against it. They are not relics. They are prototypes born from a different school of thought that valued longevity, harmony, and deep material wisdom. To study them is to engage in the most vital kind of recycling, the recycling of ideas. So as we step back from this labyrinth of mysteries, we are left not with answers, but with a richer, more vibrant set of questions. The past is not a closed book. It is an open conversation, and we have only just begun to listen. Which of these 25 puzzles speaks most powerfully to you? Does the silent city beneath the sand haunt your thoughts, or does the intricate clockwork of a 2,000-year-old computer spark your imagination? Share your perspective in the comments below. Your curiosity is the next chapter in this endless story. Subscribe to join us as we continue to seek, to question, and to marvel at the boundless, echoing creativity of humankind.